Well, this is my second video of review for test 3. I didn't quite get through all of Unit 8 on geologic time in the previous video. I did get through the first two parts, relative dating and the geologic time scale, but the third part of the unit is about radiometric dating. So I wanted to show you the important things to focus on when you're studying for test 3 regarding radiometric dating. The first of those is know how to do a problem. Let's try this problem. It says an analysis shows that a mineral in an igneous rock contains 21,000 atoms of stable isotope and 3,000 atoms of the radioactive isotope from which that stable isotope forms. Now remember, the stable isotope is the daughter isotope. There were 21,000 atoms of daughter in there when we analyzed the mineral. And the radioisotope from which the stable isotope forms is the parent. So 3,000 atoms of parent isotope in the mineral today. Now, it also tells us that the half-life of the radioactive isotope is 100 million years. How old is the rock? Well, we're going to use this hint. It says assume there were no stable daughter atoms trapped in the mineral when it crystallized. Well, let's try to work that problem. I recommend setting up a table like the one we have here. The first column for our time in half-lives. The next column is the number of parent atoms that are present. The third column is the number of daughter atoms that are present. Now, when the mineral first crystallized, that's time 0. Oops, let me make my font larger. That's time 0. There were no daughter atoms trapped in the mineral, using our hint. So how many parent atoms were there? Well, if presently there are 21,000 atoms of stable daughter and there were none in there to begin with, each of those had to come from the decay of an original parent atom. And our problem said that today we still have 3,000 atoms of the parent left. So we have to add together the 21,000 atoms of daughter plus our 3,000 radioactive parent atoms that are in there today. And that gives us an original amount of parents of 24,000. All right, well, if that's the case, then what are we going to have left after one half-life? Well, we're only going to have half of the parents, so that would be 12,000. And the 12,000 that are no longer with us, they became daughter atoms. So when there are no daughter atoms in the mineral or rock to begin with, it's always going to be the case that after one half-life we have a 1-to-1 ratio between parent and daughter. What's going on after 2 half-life goes by? Well, after 2 half-lives go by, we're down to 6,000. We're cutting the 12,000 in half, so we're down to 6,000 parent atoms left. And the 6,000 that became daughters add to the amount that were already there, so that comes out to be 18,000, and that is a 1-to-3 ratio. That's not the case today, so let's go one more half-life. What do we have here left with the parents? Half of 6,000 would be 3,000, and the 3,000 that decayed add to the 18,000 that were there at 2 half-lives, so that gives us 21,000 daughter atoms. And that's the scenario that we had in the problem, right? The problem said that the analysis shows 21,000 atoms of stable daughter and 3,000 parents. So we know that 3 half-lives went by. Our problem also said that a half-life, the half-life of our parent, is 100 million years. So 3 of those 100 million year half-lives went by. That means our rock is 300 million years old. What's the ratio of parent to daughter isotope, by the way, after 3 half-lives go by? It's 1-to-7, right? 3,000 goes into 21,000 exactly 7 times. What are some other things to remember? Well, from the radiometric dating tutorial, we saw that the answer to the question, does radiometric dating work on all rocks, was no. Radiometric dating works best on igneous rocks because we can determine the age of a mineral in the igneous rock like we just demonstrated. And the minerals in the rock form at the same time of the rock itself, so the age of the mineral gives us the age of the igneous rock. Now, we have to be careful because episodes of heating can cause our numbers of parent and daughter atoms to get thrown off and not reflect how much time has gone by since the rock formed. But there are procedures we can use to identify when that has been the case. And then we have to find a different igneous rock to date. What about metamorphic rocks? Well, some of them can be radiometrically dated, and they tend to be the ones that are higher grade or maybe intermediate to high grade metamorphic rock like schist and gneiss, where the heating was so extensive it led to kind of wholesale release and reuptake of parent isotopes so that the parent-daughter isotope ratios are reflective of when that heating or metamorphism occurred. The situation is even more grim for sedimentary rocks because not very many of those are able to be dated radiometrically. The clastic sedimentary rocks contain particles derived from rocks of many different ages. So if we select minerals out of a clastic sedimentary rock, we're looking at when that mineral first formed. It's not telling us when the sediments were deposited and therefore when the sedimentary rock formed. For our chemical sedimentary rocks, they usually don't form in settings or by processes that will incorporate enough radioactive parent isotopes. So we can't do the radiometric dating on most chemical sedimentary rocks either. Now, very young sedimentary materials in which we find some kind of plant remains or charcoal or wood, we can use radiocarbon dating for that. But because carbon-14 has such a short half-life, it can't be used on materials that are older than about 60,000 years old or so. Okay, well, study this information and then continue on and review the information in Units 9 and 10.